Year 2008. Interesting cases are starting to come to the courts in Germany and the US. The case files contain the following statements. The resulting black holes will spiral out of control and swallow our world in a matter of hours, which will be the end of our planet. These experiments must be stopped immediately. Perhaps some of you may remember, the defendant was a company that started its operations in September of that year. They were scientists working at the Large Hadron Collider at the CERN laboratory in Geneva, Switzerland. At the time, people around the world were talking about this possibility and were seriously afraid. And they were not wrong. Isn't the possibility of the world suddenly being swallowed up by a black hole a truly terrifying scenario? It's a story rarely seen even in science fiction movies. Of course, conspiracy theorists had their day, and they were pumping this fear as they do today with 5G and similar developments. Now here are the facts we have. Is there an attempt to create a black hole at the Large Hadron Collider? Yes. Is it possible? Yes. Could a big black hole on Earth swallow the Earth? Absolutely. But that's not how it works. Let's talk about it. Before we talk about this possibility, let's pick up where we left off at the end of the previous video. If you remember, it took decades for scientists to accept the black hole phenomenon by saying, okay, I'm convinced there must be such a thing. Now it's an everyday common knowledge. There have even been lawsuits in the courts over this. How did we get to this point? And where are we going? The secret hero who got us to this point, this time from Japan, Minoru Oda, a young physicist at MIT in the 1960s. Together with his research team at MIT, he is sending a rocket with the most advanced imaging equipment of the time into space. Renowned experimental physicist Bruno Rossi was also at the head of this team. The camera on this rocket observes X-rays and gamma rays from celestial bodies in space. This had to be done with a rocket because the Earth's atmosphere and magnetic field scatter the X-rays and gamma rays that reach us. Expecting to capture X-rays similar to those of the sun, the team was surprised by the results, because some of the X-rays and gamma rays captured were unusually strong and intense. But the equipment they used could not tell exactly where these rays were coming from. They could only limit it to a very large area. And in this region, it was in the constellation Cygnus, also known as the Swan constellation. However, it was not clear exactly which stars these rays were coming from. After completing his mission and returning to Japan, Minoru Oda developed a solution to solve this problem on his own. With this device, which he called a beam collimator, he would be able to locate the incoming rays more precisely. But there was a problem, a big problem. There was no rocket in Japan in the 1960s to launch that device into space. Minoru Oda, instead of saying what the heck, he improvises and uses a meteorological device, a helium balloon, and sends it 30 kilometers up to the edge of space. They parachute the device either to the mountains or to the sea and somehow find it and bring it back every time. It takes them 4 years to work with this method, and the results they get are the same as the ones they detected before, further narrowing the region where the X-ray's likely source lies. But they sense something strange. In the region where this source comes from, there is no formation, no star, etc. that could emit such a powerful X-ray. Their work and perseverance are rewarded in America. In 1970, the world's first X-ray detection satellite, called Uhuru, is sent into space. Minoru Oda, of course, is part of this team. The Uhuru satellite is from this region, further narrowing down the source of the X-rays coming from the constellation Cygnus. And in 1971, the source of these rays was finally identified. The mission started by Minoru Oda will be completed in 7 years. Where these rays are coming from, they're coming from our sun. There was a giant blue star with 30 times more mass. But when the star from which these rays came was analyzed, a crazy discovery was made. Analysis of the light from this giant star showed that it orbited another object with a cycle of 5.6 days. To orbit such a giant star in such a short time, there had to be another giant object. And this object was theoretically expected to be at least 10 times bigger than our sun when its mass was calculated. But here's the problem. This other giant body that the giant blue star orbited was not there. It was not visible. That was just impossible. A giant star orbiting something invisible. This was none other than a black hole. the first black hole detected by observation in the history of mankind, and it was going to be named Cygnus X1. By the way, after the first findings, it was not yet certain that it was a black hole. Theoretical physicist Kip Thorne is another theoretical physicist. He makes a written bet with his close friend Stephen Hawking. Kip Thorne believed that it was definitely a black hole from the initial findings, but Hawking claimed that the calculated mass of this object was below what we call the Chandrasekhar limit, the limit necessary for a star to turn into a black hole. As you can imagine, Stephen Hawking would lose as a result of this claim, which involved an annual subscription to some journals. But it wouldn't be Hawking's first time. He would later get together with Kip Thorne and make another bet with John Preskill. But we'll talk about that separately. But Stephen Hawking made science really fun. But to give Minoru Oda another parenthesis, his years of relentless work with very limited means would end a scientific debate that had lasted more than 50 years. Then Japan started space exploration in the 1970s, sending countless rockets to study X-rays in the depths of the universe. These researches are one of the factors that cause a country to level up as a country. Through the efforts of one man, there is a lot to learn from Oda's story, both personally and socially. But now we have proof. We found our first black hole. In the years that followed, dozens, hundreds. With every spacecraft we sent, we started to see black holes everywhere we looked. There were billions of them in the universe, and they were gigantic, unimaginable, supermassive, hypermassive, containing millions of solar masses, billions of them. At some point, in 2019, a project called the Event Horizon Telescope turned the entire world into a giant telescope. We were also able to photograph a black hole with 6.5 billion times the mass of our sun, or more precisely, an event horizon. But do you know what was one of the clearest things we learned as a result of all these studies? Wherever you look in the universe, no matter which galaxy you look at, spiral, elliptical, in the center of any large galaxy, there is a black hole. At the center of every galaxy is a black hole. Mostly this is a supermassive black hole. So it's actually a black hole that makes up all the galaxies. And it's these structures that make up everything, which is one of the craziest, most chaotic and weirdest things in the universe that we don't understand. How about some fiction? Maybe. The Big Bang. It was, in fact, a supernova in another universe. But, back to reality. What is this black hole? What's inside it? What's going on in there? At this point, I have to mention Einstein again, really. I'm not doing it on purpose, but you can't explain these things without him being involved. What I'm going to talk about here are the equations of Einstein's general theory of relativity. This is what we will use to understand a black hole, or rather, it is being used. Friends, Einstein's equations of general relativity are so elegant, so beautiful. What Andrew Hamilton from the University of Colorado did. You can think of it as a coding language because the equations are written in very simple, very clear math. You can translate it into computer language and find out how much warping an object causes in spacetime with incredible precision. And Andrew Hamilton is taking these equations. A 3D program calculates the bending caused by a black hole in the most precise way. And the result is very strange. First of all, a 3D program calculates the bending caused by a black hole in the most precise way. And the result is very strange. First of all, and Hamilton draws on the spherical shaped meridians and parallels similar to those of the Earth according to general relativity. The result is shocking, like a sphere, like a planet. But there's something strange, an incredibly twisted planet with north and south poles that appear side by side. It's like an illusion, and even stranger. In this program, when you throw something into a black hole, the black hole doesn't swallow it. Isn't that strange? That's the problem. Black holes don't actually swallow. They don't. It gets weirder and weirder. The object you throw into this black hole is not getting faster and faster. On the contrary, it's getting slower and slower. It's getting slower and slower. And you know what happens when it reaches the event horizon? It stops. It just stops. It just stops there. Because at the event horizon, time stops. This is the limit of general relativity, of gravity, all the laws of physics, the edge of the universe, the event horizon, where time stops. But that's where the real trouble begins. Time stops for us there. It stops for us. What happens to that object after that point? Where does it go? It doesn't necessarily stay as it is. but we don't know what happens. But we have an idea. Or rather, someone has an idea. Stephen Hawking. The answer to this question could be the answer to everything. And the answer to this question, what's inside black holes, is hidden in a paradox. One of the most intractable and important paradoxes in history, the black hole paradox of knowledge. In the previous video, we talked about the gap between quantum mechanics and general relativity. The answer to this paradox is one of the biggest candidates to fill that gap. This paradox alone deserves another video. Let's return to the scary scenario at the beginning and briefly explain why this fear is unwarranted. The CERN laboratories are not trying to create a black hole, but small black holes. This is precisely for the reason I just explained. The particles that cause this black hole are thought to have gone somewhere. But where? To another dimension, but which dimension? How many dimensions? In other words, black holes are thought to be gateways to other dimensions. Wormholes, white holes. There is no progress yet, but there is nothing to fear from these tiny, even named quantum black holes, because they are very, very small and they appear and disappear for such a short time. That's the problem. And besides, every day, every moment, countless gamma rays and X-rays hit the Earth's atmosphere and magnetosphere, and thousands of these black holes, quantum black holes, are formed at the edge of space with the other particles they hit and disappear instantly. And since we are still here, there is nothing to be afraid of. Don't worry. To summarize, black holes. What we think of as the center of chaos is actually the source of galaxies, solar systems, planets, the keys to a universe born from the unknown. We don't yet know what lies beyond black holes, but we should be thankful for what's on this side of them. But besides that, black holes are like a door for us, a gateway to many new topics, the information paradox, multiple dimensions, wormholes, and much more. Stay tuned so you don't miss any of this. And I want to thank my supporters again, and I look forward to your support in this journey of science. In this path, we are walking together. But no matter what, as always, until we meet again, I'm glad to have you. Love.